Okay, let's quickly look at model 3.2 types of fluids and dimensionless groups. We're going to be looking at introduction, properties of fluids, types of fluids, non-Newtonian fluids, time-dependent non-Newtonian fluids, dimensionless groups, and conclusion. Not all fluids obey Newton's law of viscosity. Like we said, the fluids that obey Newton's law of viscosity, we call them Newtonian fluids. But those fluids that do not obey Newton's law of viscosity, we call them non-Newtonian fluids. These fluids are mostly fluids containing solid particles in suspension and emulsions and are known as non-Newtonian fluids. Therefore, we have basically Newtonian and non-Newtonian fluids. Like we said, Newtonian fluids obey Newton's law of viscosity. That is, shear rate is directly proportional to the shear stress. A very important feature of Newtonian fluids is that the viscosity is independent of rate of shear and time of application of shear. Fluids are characterized by a log-log plot of shear stress against shear rate. Properties of fluids. Now, fluid properties include viscosity, pressure, specific gravity, mass density, specific weight, specific volume, vapor pressure, compressibility, and then surface tension as defined. These are very, elementary and simple definitions that we all know. Types of fluid. We can generally classify fluids as ideal fluids. Of course, when we talk about ideal, we're looking at an ideal situation. So we say ideal fluid is incompressible and has no viscosity. It is an imaginary fluid and does not exist, you see. So it is an ideal situation. Real fluids possess viscosity, and in practice, all fluids are real. Newtonian fluids, we've said that, obeys Newton's law. Non-Newtonian fluids do not obey Newton's law. Ideal plastic fluids, in which shear stress is more than the yield value, and shear stress is directly proportional to the rate of shear of strain. Incompressible fluids and also compressible fluids. Now, with regards to the shear stress and velocity gradient, fluids can be broadly classified into these types. We have pseudoplastic fluids, ideal Bingham plastic fluids, non-Newtonian pseudoplastic fluids, Newtonian fluids, non-Newtonian dilatant fluids, which we are going to look at one by one. Of course, look at the chart. This chart shows how the shear stress and shear rate varies for any of these particular fluids. You can see some of them are curved, some are straight line. Newtonian fluid is passing through the origin. Ideal Bingham plastic fluid is not passing through the origin, and so on. Now, non-Newtonian fluids. You have Bingham plastic fluids. These materials possess a yield stress as a threshold stress, which must be exceeded and to begin to deform. They are different from Newtonian fluids in that their linear relationship between shear stress and shear rate does not go through the origin. Remember I said for Newtonian fluids, it goes through the origin. This shows that a finite shear stress is required to initiate flow or deformation. Therefore, the shear stress of this class of materials can be represented by this. Look at it, the threshold minus our Newton's law of viscosity, where tau zero is the yield stress and mu b is known as plastic viscosity. Examples of this kind of fluids are drilling mud, paint, toothpaste, sewage sludge, and many colloidal suspensions. We have another type, pseudoplastic fluids, which obeys equation 2, where n is less than 1. That is, the apparent viscosity decreases with increasing shear rate. Examples are high molecular weights, that solutions and melt of high molecular weight polymers, paper pulp, and emulsions. We have another type. All these types are the types we have shown in that diagram. We have dilatant fluids. These fluids exhibit rheological behavior opposite to those of pseudoplastic. So while n is less than 1 for pseudoplastic, n is greater than 1 for dilatant fluids. And we have examples here: potassium silicate solutions, starch suspensions. These are examples. So for dilatant fluids, they have an apparent viscosity that increases with increasing shear rate. Now look at, for pseudoplastic, we say the apparent viscosity decreases with increasing shear rate. So why it is decreasing in pseudoplastic, it is increasing in dilatant fluids. Now, time-dependent non-Newtonian fluids. We have thixotropic fluids. Now, this is if a fixed, shear applied to the thixotropic material, the stress first increases to a maximum and then decreases again an equilibrium value. So another characteristic of thixotropic fluids is that their apparent viscosities decrease with time of application of shear. So an important application is in paint. Paint flows when it is being applied, either with a brush or roller, but on standing, it does not flow again, it sticks. Now, the second time dependent non-Newtonian fluids is rheopectic fluids. This class of fluid shows an increase in apparent viscosity with time at constant shear rate. This means that the materials will build up, increase in apparent viscosity very rapidly upon being rhythmically shaken or tapped under constant shear rate. We have some examples: bentonite, vanadium pentaoxides, and so on. Then the last type of time-dependent non-Newtonian fluid is viscoelastic fluids. So as the name implies, they are viscous fluids that also exhibit elasticity. So molten polymers are examples of these types of fluids. Dimensionless groups. We met Reynolds number before. As we can see from equation 3, if we substitute, it has no unit. Another one is Smith's number, where mu is viscosity of the fluid, rho is the density, and dF is diffusivity. If we also substitute, it has no unit. So Smith's number is often used in mass transfer considerations. One is Prandtl number. Prandtl number PR is given by Cp mu divided by K, where Cp is the heat capacity at constant pressure, mu is viscosity of the fluid, and K is thermal conductivity. If we also substitute, it has no unit. That's why we say dimensionless numbers. The next is Nusselt number, which is head D over K. H is the heat transfer coefficient, D is diameter of the cylinder, L is characteristic length, and K is the thermal conductivity. If we also substitute values of the unit, it will have no unit. Stanton group of Stanton dimensionless number given by equation 7, the same thing, no units. And also Stanton number is given by, our Stanton group is given by equation 8. That is the Nusselt number divided by the product of Prandtl number and Reynolds number. We also have Grashof number given there. If we also substitute, there is no unit. And we said that the Grashof number is the ratio of buoyancy forces to the viscous forces. This also is used in terms of determining whether the boundary layer, just like our Reynolds number, this one is also used in flow or fluids. There are other many, dimensionless groups. Many of them, in fact, we're still going to meet that in mixing and agitation, where we have the Weber number, the pumping number, and so on. There are so many other dimensionless groups. Thank you very much. We've come to the end of this module. We've looked at properties and types of fluids. We looked at non-Newtonian fluids, time-dependent non-Newtonian fluids, and we also looked at some dimensionless numbers, Reynolds number, Smith number, Grashof number, and so on. I'm expecting to see you in the next class. Thank you.